Yeah, thank you. Thank you for the nice introduction. And thanks for organizing this very nice, exciting event. And I'm very honored to talk about some research and related for security and privacy for machine learning. So today I will mainly talk about trustworthy machine learning from a separate pillar view about robustness, privacy generalization, and some like fairness. And we know there are many, many pillars. But I want to say, like, underlying they have their interconnections, and we can try to uncover their interconnections and see what else we can do to by doing one to help the other. So at the beginning, I think I don't need to re-emphasize how important or how popular machine learning is, which is ubiquitous in the world currently, like including autonomous driving, medical healthcare, smart city, etc., etc. And however, we know that even such powerful machine learning platform techniques, algorithms have brought us a lot of security and privacy problems, including one of my favorite example is that in 2016, the Associated Press Twitter account was hacked with phishing emails saying that, okay, the White House has been attacked, which triggers the atomic trading bot to dump a large amount of stocks within seconds and swipe about $136 billion within seconds, which is happened in real world already. And therefore, a lot of people ask, what are the real world examples of, say, adversarial attacks, adversarial behaviors in real world? And I would say this is one, and it even happens far before we realize the vulnerabilities of deep learning and machine learning. And currently, we also see a lot of examples from Google and Amazon about the toxicity, fairness, all kinds of issues for the large language models or chatting bots. So I would say it's indeed a time for us to join together and try to explore and understand the security as well as privacy perspective of machine learning and other important consequences. So that's why, as we just mentioned, as a quick summary, we indeed living in a very lucky world to have a lot of convenient platforms and algorithms and models, and also like abundant of data sets that we can leverage to tune and try out and explain our machine learning models. But we are still living in an adversarial environment. Therefore, as we can see, based on the previous examples, that a typical machine learner still have a very hard life to make the machine learning platform or algorithms or applications secure and private and fair and all the good properties that we want to achieve under trustworthiness umbrella. So therefore, we need to try to get together, understand like the underlying causalities on the adversarial behaviors, strategies, and try to improve, safeguard our machine learning models and platforms. So then one quick question we may want to ask is, what if we get the opportunity to ask only one question, right? The fundamental question about that we want to ask and we want to explore and we want to address in trustworthy machine learning, what would that be, right? So to me, after like a couple of years of research from different angles, I think from my personal view, I think these slides, recently I come up with it and also show in a couple of talks. I think this slide may be one of the most important slides in all the slides that I will show later. So I would say, to me, I feel in general, considering all the potential topics under trustworthy machine learning, one fundamental question indeed we want to address here, or even future, maybe close the trustworthiness gap under the distribution between the training and the testing, or like different types of distribution that we will explain later. So for example, concretely, we can see from the robustness perspective, right? We are indeed trying to close this distribution, like differentiation gap under the adversarial scenario, which is, for example, considering, say, the training time attack, we usually are called the poisoning, backdoor, etc. And I think previous talk also mentioned it. And this lead to the adversarial manipulation about the training time, right? For example, in Netflix, in Yelp, you can create a fake account and inject fake instances to poison the training process. And this lead to a bunch of pillars and topics under it to how to provide both empirical and theoretical guarantees of the model given training time adversary present, right? And similarly against the testing time attack, which we call adversary attack, adversary examples, and I think many of you have heard about these words like for a long time. And indeed, it's also just a core matter of case for understanding the testing time adversarial manipulation, which like the manipulation satisfy whatever properties like stealthiness, distribution closeness, instance level, like say LP norm closeness, all these nice properties of distance measurement. But in the end, we want to understand the adversarial manipulation for the testing time and close this gap to fulfill the robustness pillar to about the trustworthy machine learning gap. And similarly, I would say even under the privacy pillar, it's still following the similar principle, which is in the end of the day, what is privacy, right? So mainly from the like adversarial perspective, what we have is giving a model or given a model trained on certain distribution, all the privacy attacks, including membership and model inversion or other types of privacy attacks, we want, in the end of the day, we want to infer some properties of the distribution itself, right? Either instance level or distribution level, or even from model like level, like a proprietary level. Like if we want to learn the secrets of the model parameters, which is trained under certain distribution. So exactly we want to unleash some secrets from the data distribution that is used to train the model from the privacy perspective. And under this principle, indeed, if we want to make the model privacy preserving, satisfying certain privacy guarantee, for example, differential privacy, then we can start from this principle and trying to protect the model and the process, for example, data generation process. And the last one, but not the least, is the generalization, which is one of the ultimate goal for machine learning, right? But even for generalization, I think it's quite close, tightly connected with robustness and privacy as well, surprisingly, which is, I know this can be another like topic that people are trying to analyze generalization, but in the end of the day, we can see, for example, in terms of the relationship between robustness and generalization, it's essentially just the distribution under different conditions for its shifting. One is under worst case adversarial condition, one is under natural shifting conditions. And after this, we can see all the like measurements or the principles that we used before, for example, for robustness to measure the closeness of the shifting, measure the closeness of the manipulation or the like the generalization of the instance level, it's also applied to generalization as well. The only difference is that we may have different levels of say adversarial levels or the drifting strength levels to measure these two things. Therefore, I would say, although we actually have a lot of work under each pillar currently, actually there are a lot of interesting underlying connections among all these pillars. I think to me, I feel like uncovering each underlying connections would largely help to like improve every other topics, including fairness, right? Recently, we use some generalization and the robustness certification to certify the fairness, not only on the representation level, but on the end-to-end model performance level, right? And what does that mean, right? I would say that's all following the principles under this core distribution trustworthiness gap for all the topics. And for example, I want to give some quick example for their relationships, but for more details, I would be happy to discuss later on. And for some interesting findings, for example, between robustness and generalization, and we have a work to prove that these two are actually indeed bidirectional indicator for each other under certain mild conditions, which means, for example, we know under robustness, there is an important property called adversarial transferability, right? Which is if you attack model A, you can use the same perturbation to attack model B with certain high probability, right? And we find that this adversarial transferability can be exactly a tight indicator upper lower bound for the generalization, which means if your model is pre-trained on, say, data A, whether it will generalize to data B and C after small fine-tuning or even without fine-tuning, right? That generalization ability can be exactly reflection of the adversarial transferability here, and vice versa. So it's bidirectional. So the proof itself is a little bit engaging, but from the intuitive level, you can say it makes sense and it's very helpful because we know currently training from scratch about a model is very expensive, right? So what we essentially, I think in the future, what people will do is we download pre-trained large models from PyTorch and TensorFlow hubs, etc., and we fine-tune the models. But now there are thousands of models, so which model we should download and fine-tune for our own task? Right, that's very expensive. We cannot try every model, then get the selection. So whether or not we can use, say, a cheap measurement for robustness, adversarial transferability to indicate which model we should download and fine tuning to reflect the generalization here, that's a very practical usage for it. And that other usage for different directions as well. And for example, from the robustness and the privacy perspective, we actually prove under, say, federated learning frameworks that still, if you satisfy, say, epsilon delta differential privacy, you can exactly represent the robustness of that model against the training time attack as a function of the epsilon delta, which means these two have strong connections and you can use one to reflect the other. And similarly for privacy and generalization. So I would say there are a lot of things to be uncovered under this whole circle, I would say. And we actually did some like small works for each milestones. But I think as a community in this talk, I think everyone is under this security and privacy machine learning community. That would be a very nice joint effort to try to unleash the underlying connections from different pillars, including fairness and toxicity, other things. I didn't list it out, but I think naturally and intuitively you can see the underlying connection. So in this talk, so what I just said, I think is one core message would be helpful for us as a whole community to contribute to the trustworthy machine learning area. And in this talk, I will mainly focus on each pillar, like the robustness part, to introduce some recent and long approaching effort we are working on using knowledge and logics and reasoning to improve the robustness of a machine learning model. And then I will touch a little bit about privacy in terms of privacy preserving data generation models, which can be more flexible for different downstream machine learning tasks, and a little bit about generalization, which can use, say, certain Shapley value I will introduce later to measure the generalization ability of different models. And then we will see this thing that we'll introduce later can be exactly used to debug all the properties before, debugging like which instance contribute to low robustness or which instance contribute to high fairness things, so that we can come back to see which instance is more important, contribute more, and we can like better leverage or remove or clean up the bad instances. And such thing can be not only debugging on the instance level, but also on the framework level. Say if you have many like feature extractor component in a long machine learning pipeline, that you can use it to debug the importance of each component as well from the system level. So yeah, I would say maybe I will use a little bit of time to talk about it, since I think it's very interesting and useful. So, okay, come back to our robustness. want to first of all use 5 minutes to go over some issues we see recently, and maybe many of you have seen it, and that's great. And if not, we can have a quick recap to see how severe the robustness issues are currently, right? So I think hopefully many of you have seen such examples about the physical attacks against the machine learning models, right? Which using the road sign as a demonstration for, say, every road sign here, like the stop sign here, are all attacked to speed limit sign by adding these types of stickers. And the right turn sign here are misrecognized and the stop sign. So this means this attack, first of all, is targeted so that it can generate the severe consequence you want, right? And second of all, such attack is very resilient against all kinds of physical conditions. Like each row here shows different like distances, angles, and lightning conditions, etc. So they are still consistent and resilient against the physical conditions. And a quick dynamic example is that you can see on the left-hand side, it's like one of the perturbed sign we showed before. And from the caption, we can see that it's always misrecognized as a speed limit sign, which is quite dangerous that your car will never stop, right? And in addition to this classification model, there are examples of like object detection model that we did, which is you can still optimize some stickers on the sign, and you can see against this white box model, fast RCN, you can never recognize a stop sign. However, you can recognize all the other objects clearly, which means it's very stealthy and it's very hard to debug that this model have problem. Unless you go to super close to this sign and you find the letter and you identify this, right? But first of all, this is too late. And second of all, we purposely do not cover the letters so that you can indeed be stealthy about, like a human cannot recognize its perturbation, right? And this is an example about a white box. And people always ask interesting question about black box, right? So what if you don't know the model, the data, the parameters, the gradients? Can you still optimize such a perturbation, right? And very possibly this is a black box against another YOLO object detection. Similarly, we can see it can never recognize the sign until you go to very close because you recognize the letters, which is very too late for a car to stop. And in terms of this black box attack, there are a lot of interesting things. Since this is a real-world demonstration about transferability, as we mentioned, and theoretically, we can actually provide the upper lower bound of the adversarial transferability under certain conditions. So it provides a promising way for us to develop related defenses using, say, ensemble model. If you can control the transferability to be low against the different individual models within ensemble model, it's possible that the ensemble model will be robust, right? But if you cannot control such adversarial transferability, it's very unreasonable to say that ensemble model would improve robustness. It will not, because you can see such adversarial transferability is very realistic, right? And this is very interesting and there is a lot of social attention, like this sign is currently in the Science Museum of London for exhibition. And but this sign itself as a demonstration is only for road sign, which is a planar object, right? And yeah, I want to give a quick example, say not only about such a planar object, but about like the 3D real world object, right? Say against a LiDAR system. This is an example that if you drive an autonomous driving vehicle towards this 3D optimized adversarial object, which is of kind of weird shape, but it's not that weird, and with 3D printed out and then put on the road. And you can see in the LiDAR, the car never recognizes this object itself. But as a control example, if you put a box of similar size here and the car equipped with a LiDAR system will always recognize this green box, which shows that the adversarial 3D object itself, even on the LiDAR sensor scenario, it will be able to attack it as well. And I will not go to detail about the attack algorithms. If you are interested, we can discuss, because I want to save some time for the defense. But these are interesting examples I want to show and share together. And similarly, we can put the object on the side rather than in front of it. And still, you can never recognize this adversarial object. But as a control experiment, you can always recognize this green box clearly. So this is very interesting against both camera and LiDAR. And there are a lot of papers after this coming out say, okay, maybe multi-sensor fusion system is the future, right? As we mentioned, the ensemble model or fusion or things may make it quite robust. But a quick example is that it's actually very possible and easy to jointly optimize LiDAR and the camera together, for example. And this is IEEE security privacy paper showing that if we jointly optimize together, you can still get an object of like a little bit weird texture. This texture is for the camera, right? And the shape itself is for LiDAR to attack. And this way, if you put the object on the highway, which is a very common clone on highway, that if you under both like LG and Apollo simulation platform, if you put the object here, you can see the car will never recognize it, even equipped it with the multi-sensor fusion system. It will go through it, which is very dangerous. And as a control experiment, if it's a normal clone, the car will recognize it and stop. So I think it's a very interesting example. And yeah, sorry, I think there is a question, so I can repeat and discuss it. It's very good to have the interaction, discuss and things. So the question is the interconnection between robustness, privacy, and generalization is very insightful. There is a standard framework like dataset where the interdependence, all three can be studied together. That's a very, very good question, and also a very good future work. I think the short answer is there is some framework, methodology framework to trying to connect them. Mainly our group did some, for example, be a little bit more detailed, right? We know there is distributional robustness, which is if you train a model on distribution one, and if you know the distribution shift distance, like say epsilon, for the other, you can bound the robustness of this model on the other shifted distribution, right? And under this framework, it's possible to analyze the fairness of it, which is intuitively, it's very simple, is that you can, on top of this framework, you can just add one constraint about the shifted distribution to satisfy some fairness constraints, basically balance constraint. For example, you can say, I want my distribution to shift with a bounded distance. Not only this, but also I hope my shifted distribution satisfies some balanced base rate, which satisfies fairness, right? Therefore, this framework can be used to analyze both distribution robustness and the fairness, potentially privacy. But under this framework, there's no privacy yet, but I think we can. But in terms of the data set, to my understanding, there's no such data set yet. So I think it's a very good, like interesting future work we can discuss, like for a NIPS benchmark data set. I think that's a very interesting and future direction. Like indeed, for example, this year in the NIPS benchmark data set, we developed some data set for say autonomous driving testing, for federated learning, etc., and for fairness, etc. But how to unify this interconnection like a pillar together and say this data set have some unique property to measure different like robustness, privacy, and generalization. I think that's actually a very engaging analysis and discussion. I have some like intuitive understanding, as we mentioned just now, but I don't know how concrete it can be done yet. But I think it's very valuable and interesting. Yeah. Yeah. Thank you. I hope that answered the question. That's a very exciting work, I would say. Yeah. Okay, so then, yeah, so if you want to play more examples, we put it on the website as well. And a lot of autonomous driving companies also realize such adversarial behaviors and trying to testing, trying to engage, etc. But here, with all these attack examples, right, the ultimate goal for us as a community and the researchers together, we really want to actually improve the robustness of the models or the pipelines or the frameworks, right? And this is just a quick summary about like years before for detection, defense, empirically, etc. But after this, there are many work I even cannot fill in these slides. But the question is, in terms of the empirical defense, right? As we all know, I think that there are many adaptive attacks have been proposed and attacks almost all the existing empirical defense and the frameworks and the approaches. So it's very challenging and actually we need to think more about how we can provide certain level of guarantee for robustness. Just like in privacy, we have differential privacy. So people like it, people agree with it and satisfied with it. But for robustness, can we like certify the robustness of the machine learning model so that it can be guaranteed, right? And indeed, there is a long line literature of work about certified robustness for ML. And we have a SLK paper accepting this year, showing the different like branches and methodologies about certified robustness. So on the high level, the goal of certified robustness is trying to provide the lower bound of accuracy for a trained model under certain conditions. For example, such condition could be the perturbation magnitude is bounded by certain range like LP norm, or the perturbation is under semantic transformation, this semantic is bounded, or the perturbation satisfies some distribution, shifting distances, etc. So I would say I personally really like this line of work in terms of providing the certification so that we are more confident about the robustness of the model we trained, rather than say, oh, under this testing data, our like performance is 99%, but I don't know what it will happen if the data is perturbed a little bit. That's quite dangerous, right? So such guarantee, I think, is very needed. However, there is a lot of weakness along this line as well. We can see, for example, from the certified robustness perspective, there are different branches, complete and incomplete. Complete means if you say your method show output that an instance is certified to be robust, it will indeed be robust. But if your model say, if your instance is not robust, for deterministic framework, it will still not robust. But for incomplete one, if your model output say an instance is not robust, not certifiably robust, it could be of two reasons. One is the instance is indeed not robust. The other is your model or your certification method is too loose to certify it, so that it's called incomplete, because it's just sufficient but not necessary condition. And on the high level, we can see in the end of the day, we want to solve the min-max game to provide the certification, and the min means over the model parameters, and the max over the worst case perturbation bound there, right? And therefore, this leads to different optimization algorithms and relaxations to solve this min-max, and therefore get a lower bound. But among all the branches, only this branch with the probabilistic certification currently can be scaled up to large-scale datasets such as ImageNet. So that's lead to additional limitations of this line of work, which is very useful, but it's very kind of expensive. So I think it's a very interesting and good direction that we need to try to improve. And there is a question that, is there a consensus on what is the right threat model to consider for this physical attacks? Yeah, very good question. If we want to make threat model too strong, those we can also fool humans. Should we not consider strong threat model? Indeed, that's a very good question. And first of all, I wouldn't say there is a common consensus about threat models both in physical world and the digital world. For example, even in digital world, which is relatively easy, different people care about, say, I care L2, L infinity, L1, and the semantic transformations, all kinds of threat models. And also the magnitude of the threat model, the magnitude of the perturbation is also, people hope to have as large as possible. But you can see later, I will quickly introduce the state of art as well, that if the magnitude is larger than the certification, for example, will be almost zero. right? So I would say there is no good consensus yet, but I agree that we should limit the SWAT model under any sense. And this means I would say it could be application by application or case by case or things. For example, for some scenarios, say autonomous driving is very safety critical, then we need some strong SWAT models. But for some scenario, like a certain image classification, right, and not for like a face recognition or payment, etc. Maybe we can relax it a little bit. But to me, I would say it's almost not possible to improve the robustness under arbitrary adversarial SWAT models, like a very strong adversarial SWAT model, because it's just too heavy. So we always need to constrain the SWAT model under certain cases, and we can analyze it. And as a last question, that say if the attack can also fool human, right? Whether or not we should consider it or not. I think currently under this scope, we may not consider it, because currently our scope is we hope we can make the model as smart as human, at least, or as robust as human, so that if the thing cannot fool human, they should not fool model. So that first of all, we are on the same page with AI first, right? And then I think in the next stage, indeed, we need to consider strong attacker, like some attack would fool human, and for example, some malware, right? For human, it's very hard to understand those binary code and defend them. Then we need machine learning models in those areas to try to like be robust and trustworthy. So that's again depend on the applications. And I think the key point is, first of all, the SWAT model definition is definitely depend on the application. And second of all, we need to have a SWAT model for each application, like universal adversary to be robust against universal adversary. I think that's to me, I feel it's almost impossible. Yeah. Yeah, that's either bad news or good news, because we have more principles that we can follow. So, okay, yeah, thanks for the nice question. And against the certified robustness domain, right, I would quickly bring out some state of art, so we have some feelings about it. So on small data sets, for example, MNIST, right, under L infinity norm, for example, and the certified robustness, lower bound of the accuracy meaning is about 93, and the empirical robustness is about 96, which we can see has a very small gap. So we can say, okay, on the small radius and a small data set like MNIST, this gap is almost closed, which is great, right? However, the problem is on slightly large data set, for example, CFAR, which is not that large, and on L infinity norm, like this is a threat model, right, bounded by this magnitude, then the state of art certification is only about 93, 39, etc. But the empirical robustness is very high, it's about twice for it. So then the problem for this gap is either we need a stronger certification method to fill in this gap, or we may not uncovered strong attackers yet from the empirical side to bring this number to be lower, such that this gap can be filled, right? So with this gap, it's a very good guidance for us to know what else we need to do. Otherwise, we don't know actually which direction we need to improve more and which direction is more promising. So I think this is actually very helpful state of art numbers. And against ImageNet, for example, large scale data set, in terms of the certified robustness, it's almost useless. The lower bound is 27, and this provide nothing, right? And we have a certification, actually leaderboard, to show, like, if you want to play with this area, you can see all the data set and on the different radius and all the state of our method and the implementation, everything is here. So I would say, as a community, it's really good that whenever you come up with your method, you can consider all the actual real like a state of art method and compare with them and show the strengths and weakness. So I think that will be more and more healthy, and we should definitely help to improve the certified robustness, which can provide the guarantees for machine learning models. So if you're interested, you can take a look at the leaderboard. I think so far it's very comprehensive, and we'll keep maintaining it when new state of art come out. So after this, right, I hope I can convince you that robustness problem is here, and the certified robustness is promising, but still limited, which is expensive and against a very limited threat models as mentioned in the question. So how we can improve the robustness of it, and that many different ways, right? Different research currently. So one interesting direction I want to bring up in this talk today is about using the domain knowledge and using the logical inference as an approach to integrate the intrinsic information to the machine learning pipeline and therefore improve the robustness and even the certified robustness of a machine learning model. So let me go to detail about it. So I think this part is quite interesting. So I will go to a little bit more detail about it, which is, so currently there are a lot of important, I would say notices and like sounds about whether or not we can integrate reasoning into a machine learning model, like a statistical machine learning model, right? To me, my personal philosophy along this direction of work is that I feel along all the robustness in PureCore and certification we mentioned it before, all these models are based on pure data-driven statistical models, right? And I think currently they reach some bottleneck because in the data, there are a lot of information that are not modeled or represented by the data, right? For example, why our human is robust, right? Like human cannot be easily attacked for this simple like adversary perturbation or things, is that human have our logical inference and have our knowledge, and we know a cat cannot swim or all these things, right? But the machine learning model does not know. So to me, I feel we really need to integrate the reasoning and the logical analysis together with the statistical models, such that we can leverage the good, like powerful representation of, say, neural networks, together with more or less traditional AI logical inference, but now it's not purely based on the logical. We still need the statistical representations as an assistant together as a like hybrid integration pipeline, so that it can take advantage of both and get a like pipeline to achieving good property like robustness, privacy, fairness, all the different properties. So this is one way I'm doing, and I believe there are many other ways as well. And I would just say one example, and I hope this can help in like inspire other nice ideas. So basically, to us, we have one work in the sense we call it the sensing reasoning, and the sensing means in the sensing part we still use all the statistical models like Markov the neural networks, SVM, logistic regression, whatever you want, right? And instead of taking the end-to-end model itself, we take the input of it. The input can be attacked or not, and the output of it will be connected to a reasoning component, which can be realized by probabilistic language, like probabilistic graphical models. For example, Markov logic networks, Bayesian networks, etc., which can integrate the logical rules in their structures. Right. For example, later I will give a quick example that these connections will represent some knowledge rules coming from human or knowledge base or whatever. And based on this end-to-end sensing reasoning pipeline, you can take the input, and here you will have some certification or robustness guarantee based on the single neural network, based on the existing literature, right? And the hard part is how we can get the certification of this reasoning component, right? And then with this, we can get this end-to-end certification from the input to the output. So this is a high-level structure and the goal. And hopefully everyone gets the intuition here. And then I'll go to a little bit detail about the challenges and the opportunities. And the challenges for such a sensing reasoning pipeline is that, for example, for MLN, right, we know the probabilistic graphical models, the inference time is sharply complete. It's very expensive, right? And how we can address that. But however, the nice thing for the opportunity is that, as we mentioned before, in the end of the day of robustness, we want to solve the min-max game, right? But for neural network, it's non-convex and non-concav and like very complicated. It's very hard to solve the min-max game. But here with PGM, right, they define some very nice exponential family, and the parameters could be non-negative. So you have some nice properties you can leverage potentially to address, to solve some min-max to a certain extent, right, and then provide good certification. That's actually a very good opportunity among the inference part. Therefore, take this challenge and opportunity in mind, let's look at a concrete example about how we can build it and what it can achieve, right? So basically, we can see, given the input, you have different types of sensors. The sensors can predict whether it's a dog, it's a cat, it's an animal, etc. And the reasoning part give you the knowledge, which is the dog, for example, is definitely an animal, and the cat is definitely an animal, right? And if, say, some sensor attack, say this sensor tells me this is a stop sign, right? And then based on this knowledge, I know a stop sign is not an animal, right? I know something is wrong, and it will be feedback to re-improve the prediction probability of the sensing part automatically. And in this way, with such knowledge, simple explanation, we can train the weights in the sensing reasoning part, and we can train the model like the sensing part here, and then we'll have different weights for them. And then if we build up this sensing reasoning pipeline, the end goal of us is to upper lower bound this final prediction probability so that we get the certification of this pipeline. So that's our ultimate goal, right? Our first goal is integrate sensing and reasoning together as a machine learning pipeline. And our ultimate goal is we can calculate this, which is Z1 divided by Z2, and the Z1 means in this reasoning component, what's the correct assignment that satisfies the knowledge rules, right? And Z2 means all the possible words. And this is a prediction probability. And we want to upper lower bound it so that we get the certification. And first of all, this problem is hard, right? We can reduce the famous counting problem to the robustness problem. So it's Sharpie complete, right? And directly calculating it is hard, right? In CS, we always first know how hard the problem is, right? We get the hardness result. And then based on it, we know, okay, we cannot get a polynomial time, and then what assumptions we can make and what algorithm we can come up with. So that's the exact routine here. So first of all, we know it's hard. And second of all, we know it's impossible to get a polynomial time for it then. Let's consider whether or not we can have an oracle for it so that we can get the certification. So very nicely, quickly, I want to show that we can actually get an oracle for our the output of the reasoning component. And the oracle is represented as the ground truth, which is hard to get, plus a noise perturbation. That epsilon is our perturbation and the lambda is our coefficient, right? And based on this, we can see that because remember, we want to upper lower bound Z1 divided by Z2, right? And if we take a log, it becomes Z1 minus Z2. And in terms of the upper lower bound, exactly it will be calculated as a max minus a mean here, or the mean minus the max here to get the upper lower bound, right? This is quite straightforward. And the important part is how we can get this Z delta for the oracle here. And very nicely, we can actually prove that for this coefficient here, if it's larger than 0, this actually oracle here is exactly monotonic. Either it's increasing or decreasing, like larger than 0 is increasing and smaller than -1 is decreasing, so that we can always get the mean and max at the boundary of the certification magnitude there. So that's very nice. But if the lambda is between -1 and 0, we can prove this oracle is always convex. So we can always achieve the max and mean at the point and use the first order optimization to get it. So with this, actually we solve the problem, which is with certain oracle, and we break down the parameter space, and we can search over different parameter space and get the end-to-end certification for the sensing and the reasoning pipeline. Great. Is there a good question is there a trick about where do we split the statistical processing and stack the reasoning component? Is it after the primitive layer in common? Oh, that's a very good question. So maybe I'm not clear. So basically, we didn't stop at certain layer of the statistical model, say neural network. We actually directly use the final output of the model, which is the probability of all the instances. This model tells us that this is a dog with the highest confidence, and we directly input this confidence distribution to the reasoning part. The reason is this one have meaningful, like a physical meaning, right? Some layer in middle, we don't know the physical meaning. And this output has the physical meaning. So with this physical meaning, we can connect with the knowledge, say dog belongs to animal, because we need this physical meaning. And another byproduct of it is you can see not only this improved robustness, which we'll show later, but also it gives us some explanation power, right? For example, if we know when we come back, look at the reasoning part, we know, oh, this sensor is wrong because it's violated some knowledge. So actually we use the last output as input. Yeah, hope that answers the question.
Yeah, thank you.
Yeah, thank you. So, okay, so with this, I think the example I show is macro logic nets, and it can be generalized to other like Bayesian nets and etc. And want to show some quick result to see how powerful it is. So this is a very interesting like ImageNet and subnet called PrimateNet, and we have two types of knowledge of it. One is a hierarchy, which means if you are greater a pay, you should belong to a pay, right? It's a hierarchy. The other is exclusive knowledge, which is if you are greater pay, you should not be lesser pay, right? And these two types of knowledge can be represented as a first order logic like this, right? And this first order logic can be embedded into the MLN to build up the MLN program, right? And with this, we can build a sensing model to predict all the the leaf node here, and the task is to classify all the leaf node. This is a ImageNet dataset, and the reasoning part will encode all the knowledge like these two types. And only with these two, I would say very simple knowledge, right? We can see two observations from the result. First of all, there is no longer trade-off between accuracy and robustness. We know that there is always a trade-off between accuracy and robustness, right? And that's because, say, if we use adversarial training or other ways, there is a trade-off. But here, why we didn't observe that, it's also very natural because we inject additional information, right? We inject knowledge, inject things. So we indeed should achieve more. So we can see with knowledge and without knowledge, the benign accuracy here actually like this alpha equal to 0, and this is magnitude of the perturbation. So if it's 0, it means a benign accuracy. So actually with knowledge it slightly improves. There's no trade-off. The benign accuracy even improves. And let's look at the certified robustness. So for the certified robustness with knowledge, this compare with without knowledge, which is the state-of-art single neural network using randomized smoothing, which is a well-known certification. And the sigma here shows the smoothing parameters, maybe everyone know. And the alpha here shows how many % those sensing models we randomly attack, right? And you can see the certified robustness means how many the output is not only consistent before and after attack, but also the same with the ground truth, right? And certified ratio means you only need to be consistent, and it doesn't matter it's the same with the ground truth or not, right? This is a standard bench, like the matrix. And you can see by comparing the certified robustness with and without knowledge, it dramatically improves. It improves like almost twice, which is quite I would say impressive, because in terms of certified robustness, usually the improvement is like 5% of things is already large enough, but here is improves like 30% of things, which to me I think it's very promising. And you can see this pipeline is agnostic to data type, to attack type, right? Because it's knowledge, you don't need anything, so you don't need to know what types of attack strategy you are using. You only need to know the bound of the magnitude, of course. And therefore, it can not only be for image, but also for NLP data. This is for NLP data, and the knowledge, it's a stock news for using news data set to predict the stock price. And the knowledge we use is simple arithmetic knowledge, say, and the price should add the end stock price. See, similarly, like improve a little bit, certified robustness improve a lot, and with high confidence. So this is very interesting, and showing that the robust can improve different robustness in terms of the certificate. And of course, we have other different for NLP model as a benchmark for leaderboard, like the reinforcement learning. So basically, you can choose different game and different let me quickly show example. So you can choose different game and for example, and different, you want to certify, say, the lower bound of the reward, and you do certification, and you can certify different games in terms of their using method, training method. You can use different training method, and you can compare the certification of these different reinforcement learning frameworks. So this is actually the first certification for reinforcement learning framework. And it can not only for robustness, but also for other like toxicity and other properties. And similarly, we talk a lot about certification against the testing time attack. There is a training time attack, say in federated learning, you can certify that even your training data is perturbed under certain conditions, your model is still close, meaning that your final prediction output would be consistent. And this is very interesting in the sense that because it's training time certification, this certification is on different levels. Say in the testing time certification, we only care about for instance level, where's my mouse? For instance level, how large the perturbation it is, right? And for training time, it's actually on 3 levels. One is how large is the trigger, or like basically the same with testing time, the magnitude of perturbation. And second level is within each agent, how many bad instances you have. That's the second level you can bound. And third level is, say, in a federated learning framework, how many bad agents you have. So I would say in terms of certification, here I want to go to detail. I just want to say not only against testing time, but also against training time, and also against different frameworks under different levels. There are different promising certification we can provide. And also in practice, we can leverage the knowledge to generate like not only knowledge, but also causal relationships to generate different, say, traffic scenarios, safety critical traffic scenarios, so that you can testing the safety of autonomous driving, etc., etc. So yeah, I think this is so far the robustness part I want to cover. And I think I'm almost the time, which is good that I covered the most important part I want to talk about. And maybe we can start the questions and we can discuss more about it. Yeah, thank you, everyone.
Yeah, let's, if anyone have questions, like I think you can just directly ask than posting in the chat.
Yeah, I will put the summary slides here. Basically, in this talk, I want to show everything is connected and give an example of robustness, but all the principles I mentioned about robustness can be applied to privacy and generalization, other things. So I think that's a very promising direction we can follow for the unified principles for trustworthy machine learning. Yeah, thank you.
This slide was actually super interesting. So one thing I have noted down was the sort of like the insight you gave on bidirectionality. Like there has been actually like some of you already highlighted, like works on like going both sides, like that robustness. There was even a workshop, I believe at CPR, that like the sort of like the both benefits, like highlighting the benefits of improving robustness. So sometimes improving robustness benefit generalization too. And sometimes generalization, like improving generalization benefit robustness too. So it's like just wanted to like sort of like dig a bit deeper into this bidirectionality. It's like the generalization is like it's all about deep learn, like the whole community will push this frontier forward, and should we like automatically expect that the robustness frontier will sort of like keep progressing? Like we have vision transformers now, so robustness leaderboard, like the robust bench has gone up a little bit. And I think like as the next innovation comes, I don't know, maybe synthetic data or like multimodal architectures, and yeah, like more to come. So like, is robustness going to be like sold like partially because of the innovations we will be making on the generalization front naturally?
Yeah, indeed. Yeah, I totally agree. So yeah, there are a lot of work showing, as you said, that showing the connections between these two, and we also prove that how tight they are connect as a bidirectional indicator. And indeed, many work in generalization. Essentially, we want to remove, say, spurious correlation as a simple example, right, to improve generalization. And if we can remove spurious correlation, definitely it will help robustness. That's one key that we're trying. I mean, a lot of research are trying to remove the spurious correlation in terms of improved robustness. So I totally agree. I think that's why I think connecting all of them, as you mentioned, will leverage the development from one direction to help the other, and that prevent us to reinvent the wheels, and we will as a community know more from each other. I think that will be super helpful to me. Yeah, indeed.
Yeah, indeed. Like, this is an interesting intersection.
Thanks for an amazing talk. I was really intrigued by your work on the intersection of statistical and logical reasoning. And an open-ended question that I had in mind is if the conjunction of a neural network structure with a probabilistic graphical model, is that the right way of doing this integration?
Yeah, that's a very good question. Indeed, we don't know whether or not this is ultimate way, or I would say this is one way. But I imagine there are many other ways. For example, there are a lot of weakness for this as well, like the scalability and whether or not we can. This is still expensive sometimes for running for large scale data set, and how we can get large amount of knowledge. And there are a lot of questions to ask. For example, our ongoing work, which is already on arXiv, is that we can use the graphical neural networks, which is definitely more scalable than like a PGM, right? To embed this PGM into a GN and connect that in this way. I would say that's a kind of new connection structure integration, and will be more scalable, but it will lose something. So it will still achieve end-to-end good certification, but it will lose the certification for this component only itself. So it could be less tight as a trade-off of the scalability. So I would say there are a lot of other the integration methods. I don't know what is the optimal way. So I think that indeed require a lot of effort to join together. As we mentioned before, there are also like multimodality data, and like currently all the large models leverage the multimodality data to train a good model, or how we can integrate that multimodality knowledge in this framework. For example, use neurosymbolic, and therefore we can have an end-to-end differentiable model to integrate those multi-model data as another way of integration. Yeah, I think there are many other ways, but I don't know which way is best. Yeah, I think that's worth to explore a lot. Yeah.
Thank you.
Do we have any other question? Or like, since we are already over time, maybe this is a good time to sort of like conclude this talk of the seminar. So let's thank our speaker, virtual claps or real claps, as you prefer. And yeah, like again, thanks Professor Lee for the amazing, very descriptive talk. On more of like logistic note, the next talk of the seminar is scheduled again next week on 21st, again 1 p.m. Eastern. So hope to see everyone next week. Thanks. Bye-bye.
Thank you.